Okay, so here we are. This is probably the final. Okay, I don't think it's going to be the final one. But this is spectral rotation again. Another video on spectral rotation, except this time there is now a lossless way to do it without using a frequency shifter, without using a convolver, or any of that. It's just pure mathematics. And I'm just going to demonstrate it right away. Just get straight to the point. Hello, this is some test audio from the thingy. All right, cool. That's my test audio. Let me just make it nicer so it's not just in the left channel. Let's give it some dimension expander from XFA. Since that makes it sound cool. Yeah, about that much should be good. Hello, this is some test audio from the thingy. Alright, cool. That is now test audio. Skibbity. Alright, it's gonna call it that. Now, this is where the magic happens now. I made a file. Alright, you get 4 files out of it. You get a rotated one. You get a swapped one. And you get an inverted one. So, and you get a restored version. First of all, I would like to show you the loss between the input and the restored version that you get. So I'm going to invert the phase of the restored version by pressing I on my keyboard because I set up a keybind for that. And then I'm going to mix and render these. And do you see anything here? No, nothing at all. And if you zoom in, there is actually just a bit of variance. But this is such a negligible error. This error is at minus 155 decibels. It is an extremely quiet error. This error is so quiet you will never hear it in any circumstance. That's what the error sounds like. But as you can see, it's basically lossless. The previous version of this was incredibly lossless. Low end was completely missing, and among a couple of other things. And here we see, no, it's not like that anymore. It's incredibly good. Now, I'll get into what all these other things are. So we have a rotated one, right? This rotated one is literally just what you see here. So if we get in the original, it's just this rotated by 90 degrees. You see this, it's rotated clockwise 90 degrees. So this is going to end up on the bottom side of the spectrum here. So whatever we see here at the end, that shape is right here, as you can see right here. Now, the swapped version is simply swapping the time and frequency axis. So the end of the file will actually be at the top, right near Nyquist, right there, as you can see. That is the end here. Now, the inverted version of this, let me go back to spectrum, is literally, yes, that's a word, the inverted frequency axis. This is, yeah, doesn't sound like much. This is some test audio. Yeah, the sibilance, you can just hear the sibilance since it occupies basically almost the same part of the spectrum. Mixing it, you see what that does. This is basically the same as a bit crusher, technically. Let's see if I slow it down, you'll know what it sounds a bit like a bit crusher. Yeah, so those two. Now we can try it on some music. So here's a little bit of loud music I made. And I've intentionally left this empty gap at the end here. So now we have these things now. Now we have this rotated version. As you can see, the empty silent part at the end has ended up on the bottom of the spectrum here. And it's exactly what you think it's going to sound like. That's just the rotated part of the signal. We also have the swapped version, where the emptiness at the end is at the top of the spectrum. And then you have the inverted version here, where the kicks are on the top of the spectrum now. As you can see, the transients are in all the same positions. And the restored version sounds exactly the same, and we'll do a phase inversion check, mix and render. Absolute quiet, absolute silence. And the errors, if you want to know what they sound like by normalizing them, this is what they sound like. Which could be very fun. Also, in the silence, you see basically a pole stretch or blur of the entire thing. So this is like the frequency profile, I guess. I don't know. That's not a very good explanation of it, but there you go. That's something. So now you know, and the script will be in the description. I will have the script be in the description. So yes, you get to do this by yourself. You just open this, and you will need a SciPy, NumPy, and sound file. And you just run it, you do Python, skibbity2, or whatever you want to call it, enter, and then you type in the name of the sound in here, so cw amen italian.wav, and then it'll spit out 4 files here. It will overwrite them, by the way, so just beware. You have your versions in here that are now rotated in the directory that you have just run this thing in. So maybe make a little bubble somewhere that you can run this in sort of an isolated environment. Oh yeah, this is an almond break, by the way. Yeah, that's cool. There you go. That's that. There we go. There's your spectral rotation, completely lossless, except for floating point errors, of course, but we don't talk about that. And there you have it. That's how you do it. And just one more thing, just a little complaint from me that I cut out of the last video. I don't know if anybody's ever used this. I do, all the time. It's a lifesaver. Want to zoom in on something between 13K and 11K? You can do that here by just dragging on the meter. Now we've zoomed in to 13K to 11K. You used to be able to do this on the waveform view, but you can't anymore. They have decided to remove this feature because, oh, nobody's used it, which is kind of stupid. And I want them to change that and fix it because it's ridiculous that this feature is just completely gone and that no one's able to use it anymore, because it's incredibly useful. If I wanted to zoom in on the peaks here, I can't just anymore. I have to zoom in, scroll up, and then zoom in again. Oh, and then zoom in again, and finally I can look at the peaks. That's ridiculous. You can't do that anymore. That's just my little rant about Audacity's waveform, and the video is basically over now. So just goodbye. And the real part is exactly the same, except these two numbers have different phase. So when you save out just the real part, you lose a lot of phase. So what the Hermitian function does, or whatever that is it ensures that what you're gonna resynthesize, not re. What do we see here? It's Hermitian only if the Fourier transform of f is real valued. And what is the input signal? Well, it's a real valued signal. That's it. There is no complex number. So I don't need to have a complex conjugate, which means I only need to flip the signal input. I don't have any Hermitians. Oh my god.